Okay, good afternoon, class. So this video is the video for the September 8th and September 10th classes. It's just one video this week. And we're going to continue with our discussion of kinetic energy. Another form of kinetic energy Okay, so we covered, for example, the flywheel. That's a form of kinetic energy. Um, we always want to think in terms of where energy came from, and the energy in the flywheel came from someone spinning it up, whether some person or some system, some electromagnetic system or something like that. And in the case of what we're going to talk about now. Another form of kinetic energy that's very important in the field of energy in general is wind. Um, Clearly, the wind is a form of kinetic energy. You can see very good examples of this whenever there's a hurricane and the newscaster is getting blown over by it. So it's a form of kinetic energy with a lot of capability. Now, in principle, we could calculate the kinetic energy in some sort of set of wind. Now, that would be a little weird because what you would be asking to do is to take every molecule of air and use 1/2 mv squared and sum it together to get some total kinetic energy in that wind. And to a certain extent, that's exactly what we did with the flywheel. We summed the different sections of the flywheel and added all their energies together to get a total kinetic energy. But in the case of wind, it doesn't really make sense to do that because we sort of have to define, well, what volume of air are we talking about, and things like that. And so it's more appropriate to think of wind in terms of the power in wind. And not just the power in the wind per unit area. So, what we're talking about is, okay, that the wind has a certain amount of power per unit area, which kind of makes sense. The bigger the area, the bigger the power will be. Now, what area? What were we talking about? Well, I mean, it depends on what we're doing. If if we had a, see if I can draw a boat. If we had, for example, a sailboat, right, that had some sail, all right, and let's say, just for purposes of drawing pictures here, here's the wind. Well, the area would be the area of the sail. Okay, so I want to know how much power is delivered to the sailboat. I take the power per unit area in the wind and I multiply it times the area of the sail, and that gives me the power delivered to that system. Another example, of course, is a windmill. All right, and so if I have a windmill and I have the wind, then the area I care about is the area subtended by the blades of that windmill. That I want to know how much power is delivered into that area. All right, so how do we calculate the power per unit area in wind? Well, so the way to do it is to think of it in terms of what's called flux. Now, flux is a term that refers to, and I'm going to write it this way, the things per unit area per unit time. Okay? Basically, flux is the number of things that pass a certain area in a certain amount of time. Examples of flux for example, is current density. Which, you know, since this is a course in electrical engineering, I know a lot of you aren't electrical engineers in the course. J is the current per unit area. Well, what is current? Current is charge per unit time. So J, the current density, is charge per unit area per unit time. It's the flux of charge. So flux refers to the movement of something. And now, in the case of wind, so in the equation for flux that I'm about to write, you could substitute anything for thing. Okay, what I just showed is that you can substitute charge for thing, and then the flux of charge, the charge per unit area per unit time, is the charge per unit time. The current per unit area is J, the current density, for example. Now, we'll get to what we're going to substitute for thing in a moment. But first, just generally, you can calculate what flux is by taking the things per unit volume times their velocity. Now, in the notes, in the course notes, I give a little bit of a kind of a derivation of this. You can do it in terms of you know, drawing this box and things like that. But you know, I think it's sort of more helpful just to leave it at this, because you can see based on the units that it works out. Things per unit volume, velocity is distance over time. So this has the right units, things per unit area per unit time. And you can sort of almost just sort of derive it by looking at the equation, because the more things there are per unit volume, all right, the higher the flux will be, because the more things will be moving, and the higher the velocity, the higher the flux will be, because the higher per unit time it will be. So, you know, the derivation is fun and everything, and if anyone wants to go through it with me offline, that's fine. But for purposes of here, you know, you just sort of, you know, I'm just asking you to sort of accept that this is true. And by the way, then, for those of you that have taken some electrical engineering, you know that you can then calculate J by taking charge per unit volume, rho, times the velocity, v, which in that case is the drift velocity. So, you know, flux is a very powerful equation that you can use for all kinds of things. Now, in the case of the power in wind, what is the thing? All right, okay, let's think about that a little bit. Because what we want is, we want the power per unit area in wind, and so I'm going to put a little arrow there. So that is the energy per unit time per unit area. So the thing, this is the thing. energy. And bring the chalk. That's equal to, right, the energy per unit volume times the velocity. Now, here I'm going to do a little bit of an aside that's relevant to both, for your electrical engineering courses, how you think about J, and also how you think about wind. Because in both cases, the particles involved, whether it's the electrons here or the air molecules here, have two different velocities. The one velocity is thermal, and the other velocity is the average velocity in a particular direction. So, for example, the air in this room I'm in right now has, all the molecules have a lot of thermal velocity. It's just going in all directions. All right, there's no wind, there's no average velocity in a certain direction. And so, I'm going to write wind here, but you sort of understand that that's the velocity I'm talking about. The reason why I'm bringing this up is because I wrote V drift here, and those of you that have taken some electroengineering courses, particularly in semiconductor physics, know that that's the average velocity of the electrons moving in a certain direction. So anyway, with that aside, it's sort of clear that in this equation here, velocity is the sort of average velocity, the velocity of the wind, the average velocity of the molecules in a certain direction. Now, what is the energy per unit volume? All right, that one's a little bit more tricky to think about because basically what you want to do is you want to take a certain volume and you want to think about each air molecule, all right, having a velocity in a certain direction, the wind velocity. So if I were to take the total kinetic energy of all those molecules in that box, it would be, a sum. Basically, the sum of all the molecules of 1/2 mv squared. Meaning each molecule has a kinetic energy given by 1/2 mv squared, where m is the mass of the molecule. Because they all, assuming that within the box the velocity, the wind velocity is the same for all the particles. All right, and because of that, we can then bring out the the v squared and so the total kinetic energy of all the air molecules in that box is equal to 1/2 capital mv squared, where m is the total mass of all the air molecules. Now we wanted energy per unit volume, so that's the total energy divided by the volume, so that's 1/2 m over volume, and it's v squared and then another v, so it's going to become v to the cubed. But the total mass of all the air molecules divided by the volume is just the density of air, the mass density of air. So what we come down to is that the energy per unit time per unit area, which we're going to label P, so in order to get W, the power, we multiply that times area, is equal to and I think I used rho, in textbook 1/2 rho V cubed. Power per unit area. Where rho is the mass density of air, which the numerical value for that is rho is rho air, which is 1.2 kilograms per meter cubed. Which, you know, I mean, kind of makes sense if you think about a cubic meter of air, all right, that if you could somehow weigh that cubic meter of air, it would be 1.2 kilograms. Which, by the way, if you remember your chemistry classes, you know the density of water is 1 gram per cubic centimeter. And so there's 1,000,000 cubic centimeters, and so that works out to that a cubic meter of water is 1,000 kilograms. You know, that a cubic meter of air is 1.2 kind of makes sense. Anyway, this is the equation, and this is the derivation of it. And very importantly, what you see is that the power in wind goes as V cubed. So it means that if you're going to put up a windmill, you want to put it up in a windy spot because, you know, for example, if you put it up in a place where the average wind velocity, you know, overall time is, let's say 10 meters per second, which is pretty fast wind. That'd be pretty fast wind. But let's say on average it's 10 meters per second. And then let's say you put up that same windmill in a place where the average wind velocity was only 1 meter per second, 1/10. Well, the power you would get out of that windmill in the second place would be 1/1000th of the power you would get in the windy place. So because the power in wind goes as V cubed, where V is the wind velocity, it matters a lot how windy it is, where you put it. And okay, so that's the derivation of the power in wind, where P here is power per unit area. You have to keep that straight. And I believe I'm using W for power. All right, now what I'm going to do for the rest of today's video is I'm going to erase what's on the board here. Actually, I don't need to erase all of it. I'm going to pull down the screen here and start working off of the projector. I just lost focus. Let me see if I can get focus back. Bear with me for just a second here. I may finally have to break down and buy a different webcam because the autofocus on, there we go. Okay, now keep that. Basically it has no manual focusing. It only has an autofocus. And now I see that as opposed to this morning when it was darker outside, I have a problem that there's too much light in this room. And let me see if there's something I can quickly do about this. Okay, we're just going to have to try and deal with what we have going on here. Now, let me see if I can, okay, well let's just walk through it. And I apologize for the quality here, but let's see if we can make this work. So this is just following into the notes here. What we did, we took the energy per unit volume in wind, and we multiply that times V, and we got the power per unit area there. And so that's just following up with what we just did. Now, what I'm going to do here is I'm going to sort of walk through relevant sections. I don't want you to worry about friction too much. Okay, and what we're going to do is we're just going to walk through the various sections here. And I might make a little note here and there as we go through it. I wish it were brighter. Sorry. Okay, so in this section of the notes, I'm going through the different forms of energy, basically, and the different forms of energy. Well, okay, so you know, we talked about kinetic energy. We'll talk about potential energy in a little bit, and then you know, you sort of get into more specialized descriptions that are relevant to what we're doing here. And this paragraph, or a couple of paragraphs, is just talking about heat. And what heat is the thermal energy. For example, the thermal energy of all the air molecules in this room constitute the heat in this room. And heat is a quantity of energy. And for example, you know, in the experiment where I was pushing this eraser across the board here, all right, I was supplying energy. Okay, I was pushing at a constant velocity though, and so the kinetic energy of the little eraser didn't change at all, and so all the energy had to wind up as heat because there's no place else for it to go. When we discuss your homework problem on the person on the treadmill, we'll talk about heat more. And for example, you know, when you have any system, for example, a car. Okay, let's jump ahead and talk about driving a car down the road at a constant velocity. So as you're driving a car down the road at a constant velocity, clearly you're consuming a lot of energy. And yeah, one of the ideas again behind the second problem of homework 1 was to get you used to the idea of thinking of fuel consumption per unit time as a form of power. And so, you know, you're obviously burning through a lot of gas, and so, you know, you're consuming a lot of power, and so that power has to end up somewhere because you're going down the road at a constant velocity, your kinetic energy is not changing. And where it goes is into heat. When you're driving down the freeway at a high velocity, a high constant velocity, the primary place that the energy winds up in is heating the air as you move through it. because when you move through air at such a high velocity, um, you're actually spending most of your gasoline, well, apart from losses in the engine itself, which is heat in the engine, but most of the quote-unquote useful energy coming out of your car's engine is going into heating the air as you pass through it. So heat is, is basically the end stage of any system generally of energy. Now, let's talk about potential energy. Well, before we get to, part of your homework problem was understanding that as the guy was going up on the treadmill, he was working against gravity, and so he was developing potential energy. And so potential energy is equal to force times distance, just like any other form of energy. So in this case, the force is mg, and the distance is the height, h, mgh. So for example, if I take this eraser, I'm always using an eraser, and I lift it, okay, against gravity, all right, and let's say, I did it, and the force was constant because the force of gravity near the surface of our planet is relatively constant. And so the energy I've supplied to this eraser, lifting it above where it was, is equal to mg times this distance, the height. And potential energy can be converted back into kinetic energy just by dropping the eraser, and it gained more potential energy because it dropped all the way to the floor. So potential energy, just all that means is that you're working against an elastic force like gravity. That then when you release it, you can convert that back into kinetic energy. I give another example in the notes here, because in the case of gravity, it's a constant if this is gravity. In the case of a spring, well, then you have to integrate, because this is, remember, the force is k times x, meaning the more I pull the spring apart, okay, as I'm pulling apart, the force has to increase linearly. And so the energy is the integral over the distance of kx dx, or 1/2 kx squared. So that's a case where force is not constant and you have to perform the integral e dx over the distance involved. So these are simple examples, and just sort of get us primed to talk about sort of more relevant things. Now, this is an example of a potential energy, which is that I can take air and I can compress it. For example, if I were to take some sort of plunger system and I were to compress the air in this plunger and then release it, it would pop the plunger back up, right? Because basically the air is acting like a spring to a certain extent. And so, there's different forms of potential energy. We said lifting against gravity. gravity. 2, pulling a spring apart. Okay, and there's lots of ways to, what potential energy basically means is you're sort of storing some kinetic energy. And, I give a third example is compressing a gas. This is actually a very important form and very widespread used form of potential energy, because in most large factories, industrial plants, you operate a lot of things off of compressed air. In your sort of day-to-day life, probably the example that you can think of is when if you ever go to your auto shop and the guy changing your tire, right? He has a powered wrench, and usually they're powered by a compressed air line. Although sometimes here you get electric ones. But so he plugs it in. The compressed air is able to drive a motor in that wrench, and so it's a very useful way to distribute power around some sort of working facility like a factory or so. And it's not very efficient, whereas these examples like lifting against gravity is very efficient, right? I mean, when I lift it, very little energy is wasted in performing that. Even if you were pumping water up a system, very little energy is wasted. The energy that you can recover by that water going back through a turbine, the fraction is very high. Compressed air, you get about 15%, meaning as you compress the air, you're wasting about 85% of your energy. And how it's being wasted is you're heating up the air while you're compressing it, which as we go through this, you'll find is thermodynamically unavoidable. Now, in this discussion, compressed air, I go through essentially the ideal gas law, which I'm going to try and rely upon you. You can follow along the video here with your course notes. This equation states, and this probably is a review for a lot of you, that if I take air, a certain amount of air, and I reduce its volume somehow, like in the plunger situation, that the pressure goes as 1 over the volume. And so the idea here is that this big air compressor in my factory, okay, took air coming into the air compressor and lowered its volume, okay, and so increased its pressure, and so the line or the hose coming out of this air compressor is under extremely high pressure. Well, I guess another example is like when you fill your tire at Wawa, your car tire. Okay, what's coming out is very high pressure, and obviously it can convey a lot of power, because you could put a blower on it and you could blow things around with it if you wanted to. But there are other parts to this equation. Okay, if I raise the temperature of a gas, its pressure will also go up, and as if I were to increase the number of molecules in the gas somehow, its pressure would also go up, and that leads to what I should be hopefully a review for most people here, which is called the ideal gas law, which is that pressure goes as the number of gas molecules times the temperature in Kelvin, of course, divided by the volume. And we'll be using that later. Here, I just want to say that it's, it's another example of a form of potential energy. Now, there's power and electricity. And again, I'm gonna try and let's see, how do I do this? Because I wanna continue with my discussion here. Well, let me maybe I'll write at the bottom here when we get through it. This is an electrical engineering course. Hopefully you've had some electrical engineering or some physics, and you know that if you have a charge Q and you put an electric field on it, and I'll walk through this a little bit more. The force on that charge is the charge times the electric field. So this is sort of electrophysics 101. Now, the electric field is given by V over L, where V is the voltage and L is the distance. And I'll write over here, but I'm going to erase it. All right. If I have a 9-volt battery, right, there's 9 volts between these terminals. The electric field, E, now you have to realize when I'm using E for electric field and when I'm using it for energy, is equal to 9 over whatever this distance is, which is, I guess, a few millimeters. Let's say, 0.003 volts per meter. Okay, so that's the electric field. It's the voltage divided by the distance between the voltages. What I'm doing here is I'm connecting with our basic equation. And our basic equation, this is energy, is force times distance. All right. But force, electric, is charge times electric field. Okay. Right? The force of electricity is charge times electric field. But electric field times distance is voltage. So the energy in electric systems is charge times voltage. And I'm sorry, I'm not being as neat as I can be here. Let me just see if it's, and you can read that, all right? And also, as you go through the notes, now there's a little bit more development here, but there it is. I'm using E for energy and E for electric field, but the energy in an electric system is given by the charge times the voltage. For example, in my 9-volt battery, if I took a certain charge, let's do that. So let's take my 9-volt battery, and let's say this is the plus terminal and this is the minus terminal. And now let's say I take an electron, E, and I move it to the negative terminal. All right, I mean, remember, this is a negative charge, and so I have to apply a force to do that. the energy it would acquire, the potential energy. Let's do it the other way, because I don't want to get this mixed up. Let's say I take an electron and I put it near the negative terminal. Okay, like charges repel, and so if I were to let go of that electron, it would go winging over here, and by the time it got over here, its kinetic energy would equal to 9 volts times the charge of an electron, which is 1.6 times 10 to the minus 19 coulombs. Get it? Charge times voltage. And so that would be the kinetic energy of that electron. So that's how you figure that out. Okay, it's pretty easy. Energy is charge times voltage. All right, now let's extend that discussion. So what I'm going to do is I'm going to start another little thing here. So energy, electric, is equal to charge times voltage. Okay, can we read that? Yeah, we can read that. All right. Now, if you go forward in the notes, current is charge per unit time. So, if I have a current going through a certain voltage, right? If I were to, for example, take some voltage V and hook it up to a resistor, all right, I would get a certain current, I. Now, I don't want to get bogged down in Ohm's law and stuff like that right now. We will later. I is the electrons are the charge per unit time. And so power which is energy per unit time, electric, is equal to charge per unit time times voltage. But that's just IV. So the power in an electric current is given by the electric current times the voltage over which it's across. So back over here, my resistor, if I measured, okay, so resistor, that's just dissipating power. For example, it could be an electric heater. If I were to measure that power, it would be equal to IV, where the voltage is here applied across it and current going through it. So that's a pretty easy equation. Power in an electric system is current times voltage. And I can erase this now because we've retained that down there. Now let's go on. Light. When you go out in the sun, you warm up. Power is being delivered to you by that sunlight. Power is in all light. It's just most light is not that intense as sunlight is. In full sunlight, there's, and we'll go over this more, on the surface of planet Earth, the power in full sunlight, meaning there's no clouds or anything, is 1,000 watts per meter squared. Again, we're getting to this whole area thing. I mean, you can't just talk about the power in light, you have to talk about how much area there is. And I'm not going to write that down yet because we'll be writing stuff like that down a lot as we go through. But right now I just wanted to explain to you how there is power in that light. And this isn't the course in electromagnetics, but we've sort of done enough already to understand where that power is or how it resides in that sunlight. And you know, there are lots of electrical engineering courses around here, or physics courses for that matter, that would teach you this. But if what we understand about light is that light is electromagnetic, meaning it's composed of electric and magnetic fields. And primarily the electric fields are what imparts energy. Now, what does that mean? Well, it means that the energy in light is in, you know, it's electric and magnetic fields. Mostly it's electric fields. And so, unless you have charges present, it can't deliver any of that power. Now, fortunately, there's charges in everything. And so, for example, if I go out there and lie in the sun, all right, I get warm because the sunlight, the electric field in the sunlight, is causing the electrons on the atoms in my body to raise in energy, and then they fall back down. And so it's delivering power through an electric interaction with the charges in my body. Now, so, you know, energy and light can just warm something up, but of course, I mean, we will learn later, we're not going to cover this now, that you can make what's called a solar cell. And so you can take that power in the sunlight and deliver it directly via a solar cell into an electric current. And so you can go from sunlight, where the power is in the electric fields in the sunlight, and then convert that into current, where the power is current times voltage. Now we're gonna skip that step because we have a very important column here, our next bullet point here, in our potential energy. Because what you've understood, what I've tried to convey to you, is that potential energy is essentially a form of stored energy. You know, if I lift something up against the earth, I've stored that energy that I used to do that process with. And potential energy is anything working against a force, pulling a spring, compressing a gas. All right. And the next form of potential energy we need to discuss is chemical energy. And particularly, it leads off of our discussion of light. Because, of course, you know, as we went through in the first lecture, or second lecture, I forget, we still get like 85–90% of our, well, from chemicals, we get about, you know, 83% of our energy from that we use every year. And so that's stored energy in the form of chemicals. And not in this lecture, but in the next lecture, we'll talk about you know, how we release that energy, which basically you light it on fire. But particularly the chemical energy that we mostly utilize, which is oil, coal, and natural gas. And we'll go through a lecture where we reinforce this view. That energy is stored energy. We can release it by essentially reacting it with oxygen. And where that energy came from was from sunlight, from eons ago, through photosynthesis. So energy stored in chemicals, particularly the chemicals that we utilize, gasoline or whatever, what happened was that sunlight came down and hit a plant, and within the plant, okay, there are molecules, and the sunlight can interact with the charges in those molecules to raise those molecules into an excited state. Basically, an electron on the molecule goes up higher in energy, and when it goes up higher in energy, that can induce a chemical reaction that uses that excited state to form a chemical product that has a higher potential energy. And I'm just going to leave it at that for now, because we're going to go back over and over this again. Chemistry, of course, is a huge part of this. And so chemical energy is a form of stored potential energy, and in particular, the way it can occur is through sunlight exciting in photosynthesis a molecule into an excited state, which then induces a reaction with carbon dioxide to produce glucose. So chemical energy is a form of stored energy. There are other ways of producing chemicals with stored energy, which, by the way, I mean, for those of you that are more chemistry oriented, when you have energy stored as a chemical, that basically means that you can then react that chemical with oxygen or something else to release energy, which we call an exothermic reaction, if you remember your chemistry. So not all chemicals, not all molecules store energy. For example, water. It seems, periodic, and there's variations of this, that someone claims to have an engine that runs off water or something like that. And when someone talks about any system operating with water as a fuel, all right, now there are very complicated ways that water can mediate the release of energy, but in terms of water itself, water cannot react with anything to release energy. Okay, there's no chemical reaction where water is a reactant and some product is released such with energy. So that's sort of like basic 101 of the course, is that water can't be used as a fuel. Not by itself. There are complicated ways that water can mediate the release of energy, but it can't be one of these chemicals by itself. All right, and next, sort of along the hierarchy of things, we have nuclear energy. And nuclear energy is basically the energy stored in heavy nuclei, like uranium. Now, here we could be very colloquial about this, so the way I want to leave it at this point, because we'll cycle back to this, is that there are certain chemicals, methane, that can undergo a chemical reaction that's exothermic and release energy. And so those chemicals, methane, are stored chemical energy. All right. Nuclear, okay, the one we're usually thinking about is nuclear fission, which I'll explain in a little bit. Same thing. There are certain nuclei that can undergo a nuclear reaction. What is a nuclear reaction? A nuclear reaction is where the nucleus changes nucleus. I'll show it in a second. And that nuclear reaction is essentially exothermic. Now, we're going to be talking about chemistry a lot, and really, it's the same sort of thing here, And we're sort of jumping ahead a little bit, but it perhaps is helpful for the discussion here. And maybe will help you think about chemical energy too. Because this diagram here, pull it up a little bit, is a plot of what's called the nuclear binding energy, which is basically for a particular nucleus. Now remember what a nucleus is. It's the thing at the center of the atom. It's composed of protons and neutrons. And this is, on this axis, the number of nucleons in the nucleus. And so, for example, there on the right, you have uranium. Uranium, like any other nucleus, occurs in different isotopes. It's uranium if it has 92 protons, but it can have different numbers of neutrons. They're not equal to the number of protons. And what this chart shows is that if you take those uraniums, oh, I lost focus. See, I can't point at the chart. Let me see if I can get focus back. Come on. Try to do it here. I don't know how it has this problem. Maybe it's just a particular model. Come on, focus. It seems like it's trying to. There we go. Okay. I apologize for this issue here. What happens is that when I move in front of the focusing algorithm must be very sensitive to motion. And so whenever I move in front of the screen, it tends to do it. So I'm just going to kind of off to the side here, point at the screen. What this chart is showing is that, for example, iron at the top of that curve is a more tightly bound nucleus than, for example, uranium. And so when you have what's called a fission reaction, which we'll cover in more detail later, that uranium nucleus splits into two lighter nuclei. And so the products of that nuclear reaction are further up on that curve. They have less binding energy. And that's a principle I want you to think about here, that they have more binding energy, sorry, other way around. That uranium is a nucleus that is less tightly bound, all right? And that when it reacts to produce these two fizz nuclei, barium and something else, in the middle there, those two products of that nuclear reaction are more tightly bound. And so it's like it's given up potential energy. And it's not really a very scientific analogy, but it's like when you have the reactants of a reaction, when they're less tightly bound, it's like this eraser in the earth, okay? The further apart they are, the less tightly bound they are. And so when I undergo a reaction, for example, if the reaction is drop this eraser, okay, the product of that reaction is a more tightly bound system, and so I have given up kinetic energy. And that's a useful way to think about this. So when I undergo a nuclear reaction, particular fission of uranium, the products are more tightly bound, and so it's like dropping that eraser, I give up kinetic energy. As we go through chemistry in the next lecture, you'll see it's the same thing in chemical reactions. If the result of a reaction are things that are more tightly bound, you're giving up you're producing chemical energy through that, or kinetic energy through that reaction. So now, that being said, the other reason for putting up this slide was to illustrate to you that there are basically two types of nuclear energy. Well, before we do that, first, as discussed here in chemical energy, we can trace where that comes from. For example, photosynthesis 100 million years ago. For that uranium there, where did that potential energy come from? Well, it came from stellar events like supernova events that occurred, nearby our solar system, so that when our solar system formed from gases left over from previous supernova conditions, there was uranium there, and so basically, when our planet formed, uranium and other heavy nuclei were in the mix, and so became part of our planet. So the chart illustrates that fission, that is taking those heavy nuclei on the right and splitting them, can release energy because it goes up. But what it also shows is that very light nuclei, particularly hydrogen, helium, that they can react in principle and release energy because the reactants are higher up on this curve, they are more tightly bound. And that's nuclear fusion. So nuclear fission is where you go from the right on that diagram to the middle or so. And nuclear fusion is where you go on the left of this diagram to, well, not the middle, but around there. Within our sun, hydrogen is fusing with other hydrogen to produce helium, giving up that amount of energy. There's a whole nuclear cycle where it can go further than this. The life cycle of stars is very interesting because at some point the star runs out of hydrogen, and so it starts fusing these heavier nuclei, and then eventually a star is pure iron, and it can't do any more stellar reactions, and so it becomes a black hole basically. So this shows you what happens, and the particular thing to note here is that helium-4 is very, very stable, and so when something is stable, it has a high binding energy. So the sun taking hydrogen nuclei and fusing them to helium releases a huge amount of energy. And like I say, where the energy came from in that uranium is from stellar events. Where the energy came from in that hydrogen is basically from the Big Bang, from when it all started. And so our universe has had a supply of hydrogen ever since. And going on here, and you can use E equals mc squared to calculate this, and we'll do that later when we cover nuclear energy. Now, this goes through what happens in the sun and things like that, and that's sort of and we could call 5A fission, which is uranium, and 5B fusion, which is solar, which is what happens in our sun. Now, of course, people are trying to do nuclear fusion on our planet. That's not part of the course notes, and not generally something I consider that you should put as part of your final project. We'll talk more about the final project. We can talk about nuclear fusion perhaps a little bit more later in the course. You get the idea, putting that chart back up, that the difficulty, see, when we discuss nuclear fusion, what we're going to show is that man doesn't really have to do much. You basically concentrate uranium of the right isotope in it, and it just splits on its own. The reaction occurs naturally. You have to control it from doing it too much. You get the idea that if I try to fuse hydrogen nuclei, they're positively charged, and so it takes a tremendous amount of energy to bring them together before they can fuse and release energy. And in the sun, that's done by gravity. On Earth, there's various ways